When a piano chord is struck, human ears perceive a single unified sound. But mathematically, the air is carrying a dense, overlapping data stream of multiple frequencies, all hitting our eardrums at once. For a computer to analyze or manipulate this chaotic audio, it has to systematically dismantle that composite signal into individual pieces of data. To understand how this deconstruction works, we have to reverse engineer the signal itself and build the mathematical language of wave physics from scratch. Every sound is a mechanical wave, and when sound is organized into music, it can be perfectly modeled by superimposing mathematical functions on top of each other. Translating this composite sound into data requires defining exactly 14 mathematical variables, a specific set of tools that bridge physical air pressure to digital signal processing. Sound is a mechanical wave. It requires a physical medium like air, water, or solid metal to travel. When an object vibrates, like this tuning fork, it physically pushes into the air molecules around it. This creates a sequence of high-density clusters, called compressions, and low-density gaps, called rarefactions, that travel outward. To measure this physical movement, we need two foundational axes. The first is time, denoted by a lowercase t, and measured in seconds. The second is the spatial axis, or position, denoted by an x and measured in meters. If we watch a single air particle, it doesn't travel across the room, it just oscillates back and forth. We call this physical distance from its resting state displacement, denoted by the variable y. As these particles bunch up and spread out, they create variations in air pressure. We denote this pressure with a capital P, measured in pascals. We can map this physical reality directly onto the mathematical graph. As the wave passes through, the compressions correspond to positive peaks on the graph, and the rarefactions correspond to negative troughs. By translating chaotic air molecules into time, position, displacement, and pressure, we have successfully mapped physical acoustics into a mathematically measurable domain. This diagram shows a standard sine wave representing our pressure variations. The vertical height of this wave, measured from the center line to the peak, is the amplitude, or A. Amplitude measures how much pressure the wave exerts. In human hearing, this directly translates to perceived loudness. A higher amplitude means a louder sound. We measure this loudness in decibels, or dB. This is a logarithmic scale, meaning a 60 decibel conversation carries significantly more energy than a 30 decibel whisper, and a 110 decibel rock concert carries exponentially more. Returning to our wave diagram, if we measure the physical distance between two consecutive peaks, we find the wavelength, denoted by the Greek letter lambda. This is measured in meters. While wavelength measures distance, we also need to measure time. Frequency, variable lowercase f, counts exactly how many complete wave cycles occur every single second. Frequency is measured in hertz. When frequency increases, human ears perceive it as a higher pitch. A standard tuning reference in Western music is 440 Hz, which produces the concert pitch A4. The exact amount of time it takes to complete just one of these vibrations is the period, capital T. It is the inverse of frequency, calculated as 1 divided by f. If an object vibrates at a frequency of 2 Hz, meaning 2 full cycles per second, its period is exactly 0.5 seconds per vibration. We can bridge the spatial measurement of wavelength and the temporal measurement of frequency to find v, the wave speed, or the speed of sound. The relationship is dictated by the equation v equals f lambda. At a standard 440 Hz frequency and a 0.78 meter wavelength, the resulting wave speed is roughly 343 meters per second. The speed relies purely on these geometric proportions. To make sine waves useful for advanced signal processing, engineers map this linear wave onto a circle. This diagram shows a rotating vector. As it spins, its vertical height perfectly traces out our sine wave over time. The mathematical ratio linking the linear sine wave to this circular geometry is pi. A half rotation corresponds to pi radians and the wave crossing 0, while a full wave cycle completes at 2 pi radians. Because we are now working in rotation, we replace linear frequency with angular frequency, denoted by the Greek letter omega, measuring the rate of angular change. We derive angular frequency by multiplying 2 pi by the linear frequency. A standard 50 Hz linear frequency translates strictly to roughly 314.16 radians per second in computational models. We also need to know exactly where the wave begins at time 0. This starting angle is called phase, denoted by the Greek letter phi. Here, a second wave starts at a 90-degree offset, creating a visible phase difference. Phase is critical because two identical frequencies can exist simultaneously in the same space, but if their start times are exactly misaligned, they will cancel each other out entirely. By combining all these variables, we get the master signal equation. Y of t equals a times the sine of omega t plus phi. This single equation is the complete mathematical DNA of a pure tone. A pure mathematical sine wave sounds artificial. To see what makes a real-world musical instrument sound like itself, we look at the acoustic guitar. Unlike a tuning fork, a physical guitar string never vibrates at just one fundamental frequency. While the entire string swings in a single large arc, other vibrations are happening simultaneously. The string also vibrates in halves, thirds, and fourths. These subdivisions create higher pitches that are exact integer multiples of the fundamental frequency. We call these harmonics. If the string plays an A4 note, the fundamental frequency is 440 Hz. Stacked perfectly on top of that are harmonics vibrating at 880 Hz, 1320 Hz, and 1760 Hz. This chart shows how to handle these simultaneous frequencies using superposition. This is the literal mathematical addition of multiple overlapping waves. Here is the 440 Hz fundamental, and below it, the 880 Hz harmonic. The source equation here is the sine of 440 Hz plus half the sine of 880 Hz. When these waves are summed point by point, they draw a single, jagged, complex waveform. These extra harmonic frequencies and their relative amplitudes are what give an instrument its unique tone, or timbre. It is why a guitar and a piano sound completely different, even when playing the exact same note. Any complex sound, no matter how chaotic the final waveform looks, is simply a sum of pure mathematical sine waves. Now that we know how they are built, we can take them apart. We return to our opening problem. Playing a multi-note piano chord pushes a highly complex composite pressure wave through the air and into our ears. How does a computer algorithm look at that single, messy waveform and know exactly which individual keys were pressed? It uses the Fourier Transform. This is the mathematical prism that systematically reverses the act of superposition. The transform interrogates the signal to extract three specific variables we defined earlier: which frequencies are present, at what amplitude, and at what phase. The transform achieves this by wrapping the messy signal around a circle at different test frequencies. When the wrap rate matches a frequency hidden in the sound, the signal aligns with itself, pulling into a distinct, measurable pattern that stands out from the rest of the noise. By plotting the strength of these alignments, the messy waveform is replaced by a frequency spectrum. This shift in perspective reveals exactly how much energy exists at every specific pitch, showing us exactly which notes were played. When a fast Fourier Transform algorithm processes a C major chord, it outputs these exact isolated spikes. We can immediately read the data. 261.63 Hz is C4, 329.63 is E4, and 392 is G4. This fast Fourier Transform operation is the bedrock of all digital audio processing. By isolating frequencies, it enables everything from precise vocal auto-tuning to the MP3 compression algorithms that stream music to your phone. By translating the physical mechanics of sound into precise mathematical variables, the Fourier Transform gives computers the power to read, decode, and alter the fabric of the acoustic world.